spring of 1944, I received news that nearly ended the Manhattan Project. We had spent 2 years and almost $2 billion building factories to produce plutonium. Enormous facilities at Hanford, Washington, thousands of workers, the largest industrial effort in human history. And now, Emilio Segre was telling me it was all worthless. His measurements showed that reactor-produced plutonium contained an impurity, plutonium-240, just 2 or 3%. It sounded insignificant. It was catastrophic. That small impurity meant our bomb design would not work. The gun-type assembly we had planned would fail 90% of the time. 2 years of work, billions of dollars, useless. I had to call General Groves and explain that our primary weapon fuel could not be used in our primary weapon design. But here is what nobody expected. That crisis forced us to discover something counterintuitive, something that changed everything. An atomic bomb does not work by exploding outward. It works by crushing inward first. Let me explain the problem we faced. The basic concept of an atomic bomb seems straightforward. Uranium and plutonium atoms are unstable. Strike them with a neutron, they split, release energy, release more neutrons. Those neutrons strike more atoms, more splits, more energy. Chain reaction. Our original design was called gun type. Take 2 pieces of uranium, each below critical mass. Fire one into the other at high speed using a modified artillery barrel. When they combine, you have critical mass. Chain reaction begins. Bomb explodes. Simple. Elegant. We were confident it would work. For uranium, it did work. That design became Little Boy, dropped on Hiroshima. But uranium has a problem. It is extraordinarily difficult to enrich. Natural uranium contains only 0.7% of the fissile isotope, uranium-235. The rest is uranium-238, which does not sustain chain reactions. Separating these isotopes requires enormous facilities. Oak Ridge employed tens of thousands of workers using multiple separation methods. After years of operation, they produced enough uranium-235 for exactly 1 bomb. 1 bomb. That was not enough to end a war. Plutonium was supposed to solve this. You produce it in reactors by bombarding uranium-238 with neutrons. The process is more efficient. Hanford was producing kilograms of plutonium, where Oak Ridge produced grams of enriched uranium. Then Segre discovered the plutonium-240 problem. Here is what plutonium-240 does. Normal plutonium-239 is relatively stable. It waits for an external neutron to trigger fission. You control when the chain reaction begins. Plutonium-240 undergoes spontaneous fission, without any trigger, randomly, constantly. A sample of reactor-grade plutonium emits neutrons continuously. Now consider the gun-type design. You fire 1 piece of plutonium at another. This takes approximately 1 millisecond, 1,000th of a second. During that millisecond, spontaneous neutrons from plutonium-240 are flying through the assembling mass. If one of those neutrons triggers a chain reaction before assembly is complete, you get what we called predetonation. The reaction starts too early. The material blows apart before most of it can fission. The result is a fizzle. Some energy release, maybe a few hundred tons of TNT equivalent, enough to destroy the bomb and contaminate the area with radioactive material, not enough to matter militarily. Segre calculated the probability. With reactor-grade plutonium in a gun-type design, predetonation would occur roughly 90% of the time. 90% failure rate. Unacceptable. We had two choices. Find a way to purify plutonium-239 from plutonium-240, which was technically impossible with existing methods. Or find a completely different way to assemble critical mass. We needed to assemble faster than spontaneous fission could interfere. Not in milliseconds, in microseconds. One option existed, and it sounded impossible. A physicist named Seth Nettermeyer had been working on an alternative approach since 1943. Most of us considered it impractical. Now it became our only option. Instead of slamming two pieces together, Nettermeyer proposed crushing a single sphere inward. The physics is straightforward. Compression increases density. Same number of atoms occupying less space. Higher density means neutrons travel shorter distances between atoms. Shorter distances mean more collisions per unit time. More collisions mean faster chain reaction. With sufficient compression, you can achieve supercritical conditions in microseconds rather than milliseconds. Faster than plutonium-240 can cause predetonation. But how do you crush a metal sphere uniformly in microseconds? Nettermeyer's answer was explosives. Surround the plutonium with high explosives. Detonate them simultaneously. The detonation wave travels inward, compressing the core. The concept is simple. The engineering is extraordinarily difficult. Consider what simultaneously means in this context. If one section of explosive detonates 5 microseconds before another, the compression becomes asymmetric. The plutonium squirts out the weak side like squeezing a wet seed between your fingers. No uniform compression, no bomb. We needed approximately 32 explosive charges to detonate within 1 microsecond of each other. We needed the resulting shockwave to be perfectly spherical. We needed this to work reliably every time. In 1943, this seemed impossible. In 1944, it became mandatory. The man who solved synchronization was George Kistiakowsky, a Ukrainian-born chemist with decades of explosives experience. The problem was not just timing. Even with perfect simultaneous detonation, a spherical arrangement of flat explosive charges produces an irregular shock wave. The wave from each charge starts flat, not curved. Where waves from adjacent charges meet, you get interference patterns. The compression becomes uneven. Kistiakowsky invented explosive lenses. Different explosives have different detonation velocities. The speed at which the explosion propagates through the material varies by composition. Composition B detonates at approximately 7,900 meters per second. Baritol detonates at approximately 4,900 meters per second. Kistiakowsky realized you could shape these explosives to refract detonation waves, like optical lenses refract light. Place fast explosive on the outside, slow explosive on the inside, with calculated curved interfaces between them. When you detonate the outer surface, the explosion enters the fast explosive first. The detonation front moving through fast explosive outruns the front moving through slow explosive. The geometry of the interface converts a flat wave into a curved wave. Multiple lenses arranged around a sphere, each fed by a precision detonator, each producing a curved wave. Those curved waves converge at the center. A flat detonation surface transforms into a spherically converging implosion. The mathematics required to calculate these lens shapes was formidable. Teams of human computers worked for months on the geometry. We built test assemblies using materials that mimicked plutonium's density. We used flash X-ray photography to capture shockwaves in flight. Adjustment followed adjustment. By spring 1945, we achieved simultaneous detonation within half a microsecond. Shockwave sphericity within approximately 1%. Whether this would actually compress plutonium to supercritical density remained unknown until July 16th. Let me describe what happens inside an implosion device. The sequence takes approximately 20 microseconds from detonation to chain reaction. At time zero, 32 detonators receive an electrical signal. These are precision devices manufactured to tolerances of fractions of a microsecond. The signal ignites primary explosives in each detonator. The primary explosives initiate the main charges. Detonation waves begin propagating through the explosive lenses. Over the next 15 microseconds, these waves travel through the carefully shaped lens assemblies. Fast explosive accelerates them. Slow explosive retards them. The geometry converts diverging waves into converging waves. At approximately 16 microseconds, the converging waves reach a layer of material we called the pusher. Dense metal that transmits the shock efficiently. The pusher accelerates inward. Velocities exceed several kilometers per second. Behind it, enormous pressure builds. The explosive products cannot expand outward because more explosive is still detonating. All that energy focuses inward. At 18 microseconds, the shock wave reaches the plutonium core. The pressure at this point exceeds 1 million atmospheres. For comparison, pressure at the center of Earth is approximately 3.5 million atmospheres. The plutonium begins to collapse. Under normal conditions, plutonium has a density of 19.8 grams per cubic centimeter. This is already dense. Lead is 11.3. Gold is 19.3. Plutonium is among the densest elements. During implosion, this density approximately doubles, 40 to 50 grams per cubic centimeter. Such density does not exist in ordinary matter anywhere in the universe. Neutron stars are denser, but they are composed of degenerate matter under gravitational collapse. No natural process produces ordinary matter at 50 grams per cubic centimeter. We created conditions that do not occur in nature. At double density, the physics changes dramatically. Critical mass depends on density. The denser the material, the less you need. At normal density, the critical mass of plutonium-239 is approximately 10 kilograms. At double density, it drops to a fraction of that. Our core contained approximately 6 kilograms of plutonium. At normal density, safely subcritical. At compressed density, significantly supercritical. The chain reaction begins. Here is where timing becomes crucial. Each generation of fission takes approximately 10 nanoseconds, 10 billionths of a second. In each generation, the number of fissions roughly doubles. First generation, 1 fission. Second generation, 2. Third generation, 4. This seems slow, but exponential growth accelerates rapidly. After 20 generations, approximately 1 million fissions. After 40 generations, 1 trillion. After 58 generations, energy release equivalent to approximately 1 kiloton of TNT. The full chain reaction completes in approximately 80 generations. 800 nanoseconds. Less than 1 microsecond. During this microsecond, the material remains compressed. The inertia of the imploding pusher and the pressure of the explosive products continue driving inward. The plutonium cannot expand yet. This is the key insight. The chain reaction completes while the material is still compressed. Confinement time exceeds reaction time. In a gun-type assembly with plutonium, the material begins expanding before the chain reaction completes. Neutrons escape. The reaction fizzles. In an implosion assembly, compression continues throughout the chain reaction. Confinement is maintained. The reaction proceeds to completion. After 80 generations, energy release becomes sufficient to overcome the confining pressure. The material finally expands, explosively. Now, and only now, does the outward explosion begin. The fireball, the shockwave, the destruction. The visible explosion is a consequence of the compression. Without implosion, without those microseconds of inward crushing, no significant yield occurs. So why is an atomic bomb fundamentally about compression rather than explosion? Because the explosion everyone sees is the output. The compression is the input. Consider an analogy from chemistry. A match produces fire, but the fire is not what makes the match work. The friction that ignites the match head is what makes it work. Fire is the result. Similarly, the atomic explosion is the result. The implosion that achieves supercritical density is what makes the bomb work. This is counterintuitive. We associate bombs with things flying apart, destruction radiating outward, expansion. But nuclear weapons operate by a different principle. You must first concentrate energy and matter, create conditions of extreme density. Only after achieving those conditions do you get energy release. The technical term is compression ignition. The same principle operates in diesel engines. Compress the fuel-air mixture sufficiently, it ignites spontaneously. No spark required. In a nuclear weapon, compress fissile material sufficiently, it achieves supercritical density. Chain reaction occurs spontaneously. No external neutron source required. The implosion design solved a specific technical problem. Reactor-grade plutonium cannot be used in gun-type weapons because spontaneous fission causes predetonation. Implosion assembly is fast enough to beat spontaneous fission. But implosion also revealed a deeper truth about nuclear weapons. They are compression devices. The explosion is secondary. On July 16, 1945, we tested the implosion design at Trinity Site in New Mexico. The device sat atop a 100-foot steel tower. Approximately 5,000 pounds of high explosive surrounding a plutonium core. At 5:29 in the morning, the detonators fired. 20 microseconds later, the plutonium reached supercritical density. 800 nanoseconds after that, the chain reaction completed. The yield was 21 kilotons. 21,000 tons of TNT equivalent. The steel tower did not fall. It vaporized. 100 feet of steel converted to gas in microseconds. The sand beneath the tower melted into glass, a new mineral created by the heat, later named trinitite. The mathematics had worked. Explosive lenses had produced spherical implosion. Compression had achieved supercritical density. The chain reaction had completed before expansion could quench it. Every calculation, every test, every adjustment over 2 years had been validated in that single microsecond of compression. One detail reveals how compression-dependent nuclear weapons are. The Trinity device contained approximately 6 kilograms of plutonium. The yield was 21 kilotons. If all 6 kilograms had fissioned completely, the yield would have been approximately 100 kilotons. Only about 20% of the plutonium actually fissioned. The rest was scattered by the explosion before it could participate in the chain reaction. This efficiency depends entirely on compression. Better compression means higher density. Higher density means faster chain reaction. Faster chain reaction means more fissions complete before expansion begins. Modern weapons achieve higher efficiencies through refined implosion designs, more precise lenses, better synchronization, stronger compression. The hydrogen bomb, developed later, uses an atomic bomb as a trigger. The fission explosion compresses fusion fuel to conditions where hydrogen nuclei fuse. Even thermonuclear weapons begin with compression. Every nuclear weapon ever built, from Trinity to modern strategic warheads, operates on this principle. Compress first, react second, expand third. The compression creates the conditions. Everything else follows. Let me summarize what we discovered during the Manhattan Project. An atomic bomb requires achieving supercritical density in fissile material. This triggers a self-sustaining chain reaction. The chain reaction releases enormous energy. The energy produces the explosion. The challenge is maintaining supercritical conditions long enough for the chain reaction to complete. The material wants to blow apart. You must hold it together, or compress it so fast that the reaction finishes before expansion begins. Gun-type assembly works for uranium-235, but fails for plutonium because spontaneous fission causes predetonation. Implosion assembly solves this problem. Symmetric detonation of shaped explosives produces a converging shockwave. The shockwave compresses the plutonium core to approximately double normal density. At this density, supercriticality is achieved in microseconds. The chain reaction completes in hundreds of nanoseconds. All this occurs while the material remains compressed. The explosion we see is the result of successful compression. Without compression, no supercriticality. Without supercriticality, no chain reaction. Without chain reaction, no explosion. This is why an atomic bomb is fundamentally a compression device. The implosion creates the conditions for fission. The fission creates the explosion. Compression is the cause. Explosion is the effect. The distinction matters because it reveals how nuclear weapons actually function. Not by releasing energy directly, but by creating extreme conditions where energy release becomes possible. We did not simply ignite nuclear fuel. We crushed it until physics demanded a reaction. That is what we built at Los Alamos. That is what worked on July 16th, 1945. That is why an atomic bomb explosion is actually compression, not expansion.